Okay, so let's take a look at page number 2, and we'll see how much changing of strategies we have. Let's see. So here we go. Number 7. Well, we can't say this is a special right triangle again, nor is number 8. So these are both going to be our old trigonometry problems. So remember, we're going to write some old hippie caught another hippie. There we go, TOA. And we should know how to spell SOHCAHTOA. But when I look at this is opposite, it's far away, and this is the hypotenuse, it's close. So it looks to me like we're talking about a sine, and I have the sine of some unknown value is 12 over 16. Now, if you want to, we could then hit the inverse sine of 12 over 16, and we would get 48.6 degrees. Remember, we always hit the second button before we hit the trig if we're looking for the angle. But I did also want to mention that sometimes people would look at this and go, hey, those are both divisible by 4. And so it'd give me 3/4. So now look what happens if I hit second sine, and instead of hitting 12 over 16, I hit 3 over 4. What do you know? I get the same thing. Now, because those triangles would have been similar, if I reduced it, they should have the same ratios and therefore the same angles. Okay. Now, this problem specifically asked me for the length of AB. Now, notice if you ever have two letters side by side, it's asking for the length of the segment between those. So I'm asking for that value. Now, again, in SOHCAHTOA, you'll notice that I am not mentioning the hypotenuse. So the only one that doesn't mention the hypotenuse is right here, the tangent. So I would say that the tangent of 35, notice I have the angle, so I don't use inverse trig, I use regular trig. I'm not going to hit that blue button this time. The tangent is defined as opposite, far away, divided by adjacent. So again, if we cross multiply, I would be good to go. So I need to take 12 times the tangent of 35, and my calculator says we're looking at 8.402. So I think 8.4 is probably going to be good enough for us on this one. All right, moving along. Number 9. Hey, now we got something special. Notice the 45s, notice the 60. We've got a blend of special right triangles. So I am not going to use trig this time. But I would like to mention the fact that if you did trigonometry, you would get exactly the same answers, but your calculator would provide you decimals instead of the nice perfect values with the roots. So anyway, here we go. So if this triangle right here is a 45, 45, 90, if this side is 100, then that side is also 100, and it makes this x value 100 square roots of 2. Cool, so I got one of them. That's a pretty easy one. Just it's really low on the page, so I didn't have it enough room to fit it. So 100 root 2. But now again, if this is an equilateral triangle that's sitting on top of here, which it's not 100% clear. I think this thing got like resized a little bit, so it's a little bit unclear, but that's supposed to be a 30, 60, 90. I know that if this is 100, then I broke this down and I made this side 50, which makes Z, remember the short side doubled is the hypotenuse, so that's going to make Z 100 also. And last, that's going to make Y 50 times the square root of 3. So there we go. And we finished that one. That's why I like special right triangles. They just, once you know your rules, they just come out. And then last but not least, this is the trickiest one. If we have a regular pentagon, this is going to take us a little bit of work here. So what I'm going to do is I'm going to drop a little altitude is what we call that right here. And I'm going to take 360 and I'm going to divide 360 by the 5 sides that I have. So 360 divided by 5 would be 72 degrees. So like this whole angle right here would be 72. And if I wanted to, I could go like this, and this would also be 72. And this one, all of those would be 72. But I'm just going to go ahead and take a look at this one triangle right here. And so I know that this entire triangle right here has a central angle of 72 all the way across. That's 72 degrees. So I'm going to cut that in half. and say that this angle right here is 36 degrees, because then I could just look at this one portion right here, where this is 4, the hypotenuse is 4, that angle in the middle there is 36. Now, if I could find this value x, I could say that the sine of 36 is opposite over hypotenuse. So again, if I could cross multiply, the product of 4 and the sine of 36 would be x, because remember 1 times x is x, and 4 times the sine. Because see, 4 sines of 36 would be, make this base down here 2.351. And then again, I could either use the Pythagorean theorem, or I could find this by using a cosine. And I could say that the cosine of y is the adjacent, the cosine is the adjacent over the hypotenuse. And I messed that up a little bit. I don't want to say the cosine of y. I wanted to say the cosine of 36 degrees. There we are. So just like the previous problem, if I cross multiply, I would have that this height, y, would be the product of 4 and the cosine. And I got that this height here is 3.236. Now, keep in mind, that means I am now in a situation where I have the base of a triangle and I have the height of the triangle. So I should be able to find the area of that triangle by taking 1/2. Remember, the area is 1/2 the base, which is 2.351, and the height, which is 3.236. So if I said 1/2 times 2.351 times 3.236, I think I messed that up, didn't I? 3.236. I got that the area of this little triangle right here is 3.804. But that would just be this triangle right here. But I would actually have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of those little triangles. So that means if I multiplied by 10, because it would take 10 of these little triangles to make it into that whole piece, the area of my shape would be 38.04 units squared. And hey, we're done with page number 2. Hopefully that was helpful, and I'll see you back in class.